Okay, welcome to EGR 456. In today's class, we are going to talk about trimming and linearization. So the objective of today's class, objective is understand, trim and linearization. And this information is going to be uh, looking at, we will be looking at fairly basic system, but then the objective would be, once we understand how to trim and linearize using Simulink, and then get some practical understanding of what those numbers mean, what is that linearization, how does that work, then we can actually perform the linearization and trim and linearization of an airframe. But it is not a good idea directly to jump into the airframe, because remember, there are 12 state equations. So we have 12 state equations, and it's a very complex system. So let's start with a very simple system, try to understand how we can trim and linearize, then try to understand the physical interpretation or the meaning of what is trimming, what is linearization, how does the response compare, and then I will try to give you some hints on how to solve the project problems. So first and foremost, a quick recap. And this is the same system that we have studied in the past. So what I'm going to do is, I have a simple spring mass system. This is mass M, and this is spring stiffness K. And the differential equation of motion for this system is mx double dot plus kx is equal to maybe an external force F. This is the second order system. And in Robotics-1, we looked at the transfer function representation. We looked at how to solve this system using numerical approximations and so on. But now what I want to do is, I want to talk about what happens if this system is nonlinear. So this is second order linear equation. Now what I want to do is, I want to investigate what happens when this system is nonlinear. So for an example, let's assume M is equal to 1, K is equal to 1, and let's assume that this spring, whereas this is force and this is deflection, this is sort of a hardening spring, which means force versus deflection relationship is cubic. Unlike the linear spring, if you have a linear spring, then the force deflection relationship is going to be linear. But we are talking about a hardening spring. So let's assume my nonlinear differential equation, and clearly this is nonlinear because of the cubic term x double dot plus x cube is equal to F. This is the second order nonlinear differential equation. Now, one thing we have to be absolutely certain, that you cannot take a nonlinear differential equation and find a transfer function. So what we want to do is, we want to find an approximate linear system. So what we want to do is, we want to find an approximate linear system that would be used to construct a transfer function or can be used to design the controllers. So the purpose of today's lesson is to take this complex nonlinear system of equation. The good news is this equation is second order. We will take this second order equation, convert it into simple linear equation using the Simulink equation system, and then we will trim it. Then we will use the lin mod. And then I will give you hints on how to do this exercise on the actual problem, the project problem that you have. But recognize the project problem is considerably complex because you have 12 state equations. First thing first, what I want to do is I want to convert this equation into a state space equation. So first, state space equation. Since it's a second order system, there are two states. There are two states. You start with the lowest order derivative x and go a higher order derivative x dot. So these two are the states. What it means is this system will behave in this state space. So it will have certain value of x, it will have certain value of x dot, and then you can analyze the system in this state space. So basically, you can actually see how the system behaves if you were to plot this state space. And this is also called as phase plane. So state space or phase plane. So I'm going to start with something like this. And we did this earlier, d by dt in robotics 1. So if you have any questions or concerns, I would encourage you to watch that video, x dot. Now here I have the first matrix. Then I have x dot. Please note, these are the states. Again, these are the states. So I have this equation, which is given as x dot is equal to ax plus bu. Now plus I have a b and then I have f. Now what I want to do is, first and foremost, I want to populate this matrix so that this equation can fit into this profile. So this equation, bear with me, 0, 1, so that d by dt of x is x dot, and then you will have minus 1, 0. And this equation is going to be 0 and 1. So now this equation has been written in state space. The only question is, what happens to this cubic nonlinear term? And this cubic nonlinear term appears as a nonlinear term 1x cubed with a negative sign. So what we have done is, first equation is written as d by dt of x is equal to x dot, and d by dt of x dot, which is nothing but x double dot, that comes from the equation, which is minus x cubed plus f. So this is my equation 1. This is my equation 2. So you will notice that I have these two equations written in the state space form. Now what I want to do is, first and foremost, I want to take this equation, which is obviously nonlinear, construct a Simulink code that will have this equation programmed, and then use the built-in Simulink functions to trim and linearize. Now, before I go any further, I just want to make sure everyone understood the state space representation of this nonlinear equation. Any question in this nonlinear equation? So I want you to look at this equation. In today's class, we are going to start with this equation. This equation is a nonlinear equation that is representing the equation shown over here, which is star. And we will be studying this equation in detail. Now, what I want to do is, I want you to understand this has this nonlinear term. And somehow we want to approximate this x cube multiply with f. X cube is not multiplying with f. There is a plus sign here. This is the plus sign. So if you look at this equation 1 and equation 2, does that answer your question, Ghazi? There is no multiplication, there is just addition. Okay, so cool. So now look at these two equations. Those equations are programmed. Now let me talk about, first and foremost, what is trimming. Trimming is finding an operating point. Finding an operating point. And this operating point could be either a steady state or it could be zero. So depending upon the dynamics that we are trying to study, you could have a steady state operating point or you could have a zero operating point. Now, let me pose the problem like this. So we have this equation, and I'm going to go back to this equation, which is something like x double dot plus x cube is equal to f. And I want you to visualize the spring mass system something like this. So consider the spring mass system is like a weighing balance. Okay, the spring mass system is like a weighing balance. And you have this external force F. Now my question is, what would be the value of F? So what is the value of input? What is the input for X is equal to maybe 10 units in equilibrium or steady state. What I mean by that is x dot is equal to 0 and x double dot is equal to 0. So I'm trying to find out, say you have this weighing balance, it's a nonlinear balance, and I want to see what value of F will cause this spring to deflect by 10 units. And to solve this problem, it's simple. I will substitute x dot is equal to 0, x double dot is equal to 0, and F to be found out, and X is equal to 10. So x dot double dot is 0. So 0 plus 10 plus 10 to the power 3 is equal to F. And boom, I get the value of F, which is 1010 units, could be newtons. So what it means is if I apply the external force of 1010, this spring will get extended by 10 units. Now what I want to do is I want to go back and try to kind of see what is happening with my differential equation that we started with. And I'm gonna rewrite this differential equation once again. So my differential equation in state space, the differential equation in state space is something like I have x dot is equal to, so let me rewrite that equation and then try to convert it into a suitable form. D by dt of x is equal to x dot, d by dt of x dot, which is x double dot, is equal to minus x cube minus, I'm sorry, plus f. So just for simplicity and consistency, I'm gonna say my x is equal to x1, x dot is equal to x2, and x is equal to x1 and x dot is equal to x2. So this equation is gonna look like x1 dot is equal to x2 and x2 dot is equal to minus x1 cube plus f. And I want you to think about this for a second because this is a super duper important equation. Now let me identify what's going on here. In this equation, there are two states. X1 is a state, X2 is a state, and f, and for the sake of discussion, let me say f is equal to u. F is equal to u. So that will be quite consistent with what we are going to do. So f is equal to u. So this equation is written in sort of a standard form. Now, before we go any further, I just want to make sure that everyone is comfortable with this equation. Any questions about this equation? Now, let's again remind ourselves that x1 and x2 are the states and u is the input. This equation is nonlinear. So what I want to do is I want to linearize this equation. So the objective is linearization. Objective is linearization. Now, how do we linearize? So to linearize, we can use the Taylor series expansion. And for Taylor series expansion, what I'm going to do is I'm going to show this something like this. I'm going to call this as F1. I'm going to call this as F2. And let's look at the Taylor series expansion. Or I can find out the Jacobian. So what I'm going to do now is I'm going to look at the equation and I will write this equation down as a Jacobian. So, or a Taylor series expansion, however you want to do it. So you have F1, F2 that is evaluated at the operating point, plus partial F1 by partial X1, partial F1 by partial X2, partial F2 by partial X2, and partial F2 by partial X2. So multiplied by delta X1, delta X2 plus partial F1 by partial U, partial F2 by partial U, and delta U. So this is nothing but the Taylor series expansion, or also this is the linearization about the operating point. Now, what we want to do is we want to evaluate this Jacobian and this guy, which is the external excitation or forcing. So please note, I'm going to write this over here. Partial F1 by partial X1, partial F1 by partial X1. If you have your notes, F1 is X1, X2. So this guy is going to be 0. Partial F1 by partial X2 is going to be 1. Partial F1 by partial X1, partial F1 by partial F2 by partial X1 is -1, -1, -2x1, and then there is no x2, so this becomes 0, 2x2 square, which is, let's see, x1 cube, so this will be 3 times x1 square, and then this will be 0, and this is going to be delta x1, delta x2 plus f1. There is no u in f1, so this partial becomes 0. There is only one u in the second equation, so this becomes 1, and you have delta u. So please understand, this is what we have. So this is, now this needs to be evaluated at operating point. And at operating point, x1 is equal to 10, x2 is equal to 0. So when I evaluate delta x1, delta x2 is equal to, this guy is going to be 0, 1, -1, -3, 100, 0, delta x1, delta x2, and plus 0, 1, delta u. So now what this means is I have what is the value of the first term. So here f1 is equal to x2, f2 is equal to -x1 -x1 cube plus u. So this first term, operating point, will actually be cancelled out with the external excitation, because at the steady state, this term is going to get cancelled out. So this is actually gonna go to 0. So this term is gonna be 0, 1, -301, 0, delta x1, delta x2 plus 0, 1, delta u. Now, what it means is my linear equation, linear approximation is delta x1 dot, delta x2 dot is equal to 1 0 minus 301 0 oh, 0 1 0 1 delta x1 delta x2 plus 0 1 delta u. So this is my linear approximation at operating point x is equal to 10. Now, this linearization we performed by hand. And at this point, I just want to quickly remind you that if you watch the video that I asked you to watch in last time, uh, there was an example which is called water tower. This example in MATLAB was solved in that video. Now what I'm going to do is I'm going to try to solve the similar problem for the equation that we have on the board. So before I begin, any questions? If you have any questions, you can type it in the chat window or you can raise your hand and I will unmute you. If there are no questions, the objective here is how do we perform this linearization using the Simulink? And for that, I would ask you to run MATLAB. So I'm going to switch my screen to MATLAB and then we will solve this problem step by step. So now you should be seeing my screen. So what I want to do is, first and foremost, I want to program this equation. And the way this equation will be programmed is I would first write this equation like function is equal to out, equation in the parentheses dy, dy1 is equal to y2, dy2 is equal to minus y1. And if we want to add the nonlinearity, I'm going to take this out, dy2. So this is going to be my equation that will be used for simulation. And this equation is uploaded on the canvas, but I'm just going to copy and paste this in the chat window so that you can create a file inside the MATLAB and then save this code in your command window or in your MATLAB. Now, first and foremost, I want to see how this equation runs. So to solve this problem, look at my command window. I am going to use ODE 45. And then I'm going to code, try to solve this equation numerically. Okay. So the command is t comma y is equal to ODE 45 at the rate equation 1 comma time series 0 to 5 comma initial states And I'm gonna give initial states maybe 1, comma 0. Run, and I have this output. So I'm gonna give you this code right here quickly, copy, and I want you to run this and make sure that you have the same output as my output. If you want to plot it, this is how you'll plot t comma y. And once you see t comma y, plot t comma y, you should be able to see the plot, not this one. You should be able to see this plot. So this is the plot you should be able to see, where you see the displacement is starting from 1. It's a sinusoidal sort of displacement. But again, if as you increase the time, you will see that there is sort of a hardening non-linearity, and the system would behave a little bit differently. Everyone able to get this system running? Any questions here? Okay. The plot is shifted left. I have no idea. Let's increase the time. Then plot. Not this one. You should be able to see something like this. Okay. Now, what I want to do is I want to program this same equation in Simulink. So I'm going to go to Simulink. Open your Simulink. Go to blank model. And here you should have Simulink. Do you have your Simulink open? Okay, now go to library browser, user defined functions, and grab MATLAB function. Go to user defined function, grab MATLAB function. Double click on MATLAB function, and this function will open. We will replace this function by our equation 1. Everyone got that? So this MATLAB function will now should have the syntax of equation 1, EQN1. Save, and I'm gonna give, say, trial. So now when I go to Simulink, I should have this MATLAB function. And what I want to do is, I want to numerically integrate this equation. Everyone has this MATLAB function inside the Simulink. So go to library, commonly used blocks. First and foremost, we need an integrator. So where is my integrator? And then I need a scope. So I will take the scope from here. I'll take integrator from here. Connect this, make it look nicer. Tap Y from here. And I need to add a clock. Clocks are in sources. And this is what you should have. If you want our initial conditions to be consistent, go to integrator. Initial conditions are 1, 1 semicolon 0. Click OK. Now I want to wait here for a minute just to make sure that everyone has this Simulink code. So do you have this Simulink log diagram done? Everyone? Yeah, initial conditions are 1 semicolon 0. I'll show it to you again. 1 semicolon 0. All right. Now try to run and tell me what happens. Try to run. Correct. Remember, I told you something about the data structures in MATLAB and Simulink not being consistent. If you run, Simulink would complain. And I want everyone to run this and see that you have this code, this prompt from Simulink that is telling me something is wrong here. And the reason for that is Simulink does not like the matrix data structure. So you need to change this data structure to something like this. And we did that in our earlier lesson. So you can't access a matrix vectorially. You need to change your code, and I will copy and paste this modified code. Save. Now go back to Simulink and run and see what happens. You should be able to double click on scope, and then you should be able to see the plot, which is pretty much same as the earlier plot. So this is the plot that we got from MATLAB. This is the scope from the Simulink. And I want everyone to compare these results for a minute. Now the thing that we are going to do next is a little bit interesting. So I want everyone to pay attention to the manipulation that what I'm doing. But before I do that, any questions at this point? So here is what I'm going to do. I'm going to go to library browser, commonly used block. get a demux and drag and place it over here. Tap the signal, get it from the demux, and add the scope to demux. Add one more scope. So now I will have these two signals separately. And there's a reason I'm doing this. Right click, go to view, layout. Once again, everyone, please look at what I'm doing. Open the scope, go on to layout, and then select this column. Now what it will do is, when you run the code now, it will actually plot these two signals separately. You will have x and x dot, x and x dot. So the way you do that is go to the scope, go to the view, go to the layout, and then select the layout that you want. Any questions here? If you have questions, just raise your hand or ask me question in the chat window. Now, any questions here? No questions? Everyone got this code working? All right. Now here is the objective. And I'm gonna go slowly for this next part. So please pay attention, and I will show each step 2 times. So here is my suggestion. First, observe what I'm doing, okay? And then repeat with me when I do it. So here is the objective. This equation comes from here, is a nonlinear equation because of this cubic term. Now we are going to linearize this equation using 2 techniques. One is the linear system analyzer tool, and the second is linmod, which is a MATLAB command. So first, here is what I'm going to do. So everyone, please pay attention. What I'm going to do is go to library browser, and I'm going to add tabs. So please note, there is this in. So what I'm going to do is I'm going to add this in over here, and I'm going to have out. I'm going to add out over here. So this is one out, and basically this is no, I need to take this out. I'm going to add this over here. So now what I have input and I have output. Next, I'm going to go to the apps. And in apps, there is model linearizer. I'm going to click on the model linearizer. So the model linearizer will open. And once model linearizer opens, you would have this interface. I'm going to say result viewer. I'm going to go to analysis on, and I'm going to click on model IO. So this is the model input. This is the model output. If you don't have model linearizer, that is totally fine. So you will have to go to home, then add-ons, then you go to linearizer, linear system toolbox, and then you will get all these toolboxes. So you will have Simulink control toolbox, and then you will have to download these linear control toolbox. So I have control system toolbox. So you need all these toolboxes. You will please note. Yeah, I will go back just a second. So I want you to download the aerospace block set as well, system identification, control system toolbox, optimization toolbox, all these standard toolboxes you need to download. And the reason for that is we are gonna, in the next class, we are going to use these different toolboxes. So please download all these toolboxes. Could you email? Okay, to be honest with you, John, when you install MATLAB, I would select all the toolboxes. Because we will use combinations of multiple toolboxes, and that's what we need. Yeah, then I suggest, this is for John, what you can do is you can go to a lab on ASU campus and then use our high-speed internet to download MATLAB. Yeah, I will do it once again. But unfortunately, I won't be able to give you the list of all the toolboxes uphand. Uh, the reason for that is because a lot of these toolboxes have interdependencies. So for an example, if you install one toolbox needs another toolbox needs another toolbox. So it is very difficult for me to track all the interdependencies. For an example, aerospace block set, there are some functions that use the control system toolbox. Control system toolbox uses some function in optimization toolbox. So it is not possible to come up with all the dependencies. Otherwise, when we start working on a problem, we will be able to run part of the program, and then we won't be able to run the other part of the problem. So that is the issue. Anyway, so moving on. Now, what I want you to do is uh, just look at this system and go to model linearizer, and then go to model IO, model initial conditions, click down, and then here you will see trim model. You will see trim model. Click on trim model. As soon as, okay, let's see what's going on. So model IO, model initial conditions, trim model. Let's see. Simulink cannot determine the size. Okay, so this is the classic problem here. So what we need to do is, here we need to again add a mux. So go back to simulation, then go back to mux, and then grab this mux, take it over here, you should have two display ports, and then you would have two inputs. One input is here, then another input is here. Save, go back to, and at this point, you may have to open the linearizer again. And what we need to do is we need to look at model IO. So you have two inputs and there is just one output. Then go down to model initial conditions and say trim model. And here you should be able to see all the states that are interacting with your model. So I'm going to stop here for a minute just so that everyone catches up. Okay, everyone opened the linearizer. Is linearizer system open without any errors? All right, now see what I'm doing. This is input 1. This is input 2. These are the states. So this is the x, x dot, x, x dot. This is the output, the first state and the second state. Now what I want to do is somehow I need to make the changes to the code so I can interact with this code externally. Now I want to go back to equation, and see what is happening. In this code, there is no external force. In this code, there is no external force. So what I'm going to do is, watch, I'm going to add an external force U here. And I'm going to modify this with an external force U here. So please understand, I made this change to this MATLAB function. Now I'm going to go back to my Simulink. Once I save this inside my Simulink, once I save this, I have this type of structure change, T, Y, and U. Now, in the earlier case, I said my input is going to be Y, the X, and X dot. These are the two states. But now what I want is, I would like my external state to be U. So I'm going to add this to U. And I'm going to again go back to what I was doing. And I will complete the loop. And I'm sorry, little convoluted, but I want you to understand what we did, that in the initial code, I did not have external force. I just had two inputs and one output. I modified the code so that I have external function as an input. And I have this output that is fed the scope. And at this point, you should have a system set up something like this. No, there is actually, I just wanted to show you the inputs to y because y was a state vector, but I want our external input to be u. So there is no, I just took those out and now my input is just u. My output is coming from out. So I want you to make sure that your code is exactly similar, or your script is exactly similar to what I have. Any questions here? Okay, now I will open the linearizer again. Go to apps, go to model linearizer. And now here, there is something else I want to show you, and this is super important. Recognize, and I want you to understand, recognize earlier I had two inputs going to the y. Now I just have one input going to u, which means I modified my Simulink diagram. So in that case, look at this sync with model. You will have to click sync with this model and observe what happens. Once you click with sync with this model, you are going to have one input and you are going to have one output. Go to sync with the model, click sync with the model, and now you have states, inputs, outputs. Did you get that, Alex? The button is here. So you have to go to linear analysis. You have to go to trim model, and then this option will pop up, trim the model. And then here there is sync with the model. States, input, output. A quick recap. State 1, state 2. Where is the linear analysis? You need to go to apps. And there is a model linearizer. Apps, model linearizer. Apps, model linearizer. Okay. Now, next thing, what I want you to see here is there is trimming and generate MATLAB script, but we need to provide the conditions. So the condition is our state, which is state 1. State 1 is the displacement, state 2 is the velocity. State 1 is the displacement, state 2 is the velocity. State 1 is 10. Everyone, please look at this, what I have done. So state 1 is 10, state 2 is 0. State 1 is 10, state 2 is 0. This kind of gives an initial condition. You can also start with initial condition of 1. That was the initial condition that we started with. It doesn't matter. This initial condition can be anything as long as it's close to the operating point. Now I want you to go to the outputs, and this output I want to click known and change this value to 10. This value must be 10. Scope. Okay, just a second. So value is 10. If you don't have that app, then you will have to download the app from the add-ons. So value 10. Just sync with the model. And now check this out again. Your states, this state 1 can be 1, 2, 3, all the way to 10. State 2 can be 0. This is the input, this is the output. And now I want you to start trimming. Click on this button, and then you will see this dialog box open up. And unfortunately, something has happened. It's saying that it cannot find the state. So let's go back and now change this a bit. Change this a bit. And again, start trimming and see what happens. And boom, you found the optimal point. So it says that optimal point has been found, that is OP trim 2. Double click on OP trim 2. And you will see the output. And in this output, I want you to see this output is 10 and this input is 10, 10, 1010. Remember, this is the answer that we got earlier. This is the answer that we got earlier. Okay. Now I'm gonna redo this exercise again, just so that everyone understands. So this was the first time. Now let me show you what I did again. Starting from the very beginning. So initially we had 2 inputs, and that input was mapped onto the workspace. Now what I did, I changed my Simulink diagram. So I just have 1 input, that is the external input. I have an output, that output is integrated, and I get the displacement here and the velocity here. So if you click on here, you're gonna get displacement and velocity. Now, once again, follow my lead. Step 1 is you should have this model linearizer toolbox in your apps. You can also use the linearization manager, but I would start with model linearizer. So click on the model linearizer. Once model linearizer opens, you will see that it has multiple workspaces. There is a MATLAB workspace, there is a linear analysis workspace, and there is variable preview. Now, please follow my lead. This is super duper important. I want to visualize the results. So result visualizer. Then I need to go to analysis, click on model IOs, click on model IOs. Then I want to trim. So operating point is not the initial condition, but the operating point is the trim point. So go to trim. Everyone with me so far? Go to trim, click on trim. As soon as I click on trim, as long as all my inputs and outputs are mapped properly, this thing will open up. For some reason, if you make changes in your Simulink file, the way I did before, you will have to click sync with model so that your model parameters are captured properly in the trimming tool. Now let's see what these are. This is the state 1. This state 1 is X. State 2 is X dot. Now you may ask me, where is this 1 coming from? This 1 is grabbed from the integrator. See the initial condition 1, 0. This 1 is coming from the initial condition. You can change this as long as this is a numerical routine, which means as long as you start anywhere near the operating point, your solution will converge. Otherwise, the solution will not converge. Now look at the inputs. This channel 1 is nothing but U. Channel 1 is U. Output. Channel 1 is this guy, out 1. We want our output to be 10. So our output is known. So I'm gonna say 10. And just sync with the model and then go back. And here I'm gonna start trimming. Start trimming. Assuming everything is good, a trim point will be found out. Click on the trim point. And please note, in this trim point, you will see that to get the output of 10, the desired value is 10, actual value is 10. I need to supply the input of 10, 10. So which means this numerical trimming matched with our analytical trimming. Any questions at this point? Any questions? Everyone got the same value? 10, 10? Wow, it should not be different. Okay, you want me to go through the code again, Travis? Or maybe I can explain this during the office hours later because I want to show the linearization real quick. Now, next part is super duper important. So everyone pay attention. Here is what you're gonna do. Go to U, highlight the arrow, right click, go to U, highlight the arrow, right click, and go down to linear analysis points. Everyone with me so far? The linearization tool explicitly needs what is the input and what is the output. So then click, since this is input, click on input perturbation, and then you will have this teeny tiny arrow showing input perturbation. Go on to output, same drill, right click, go to linear analysis points. This is the output measurement. So click on output. And now you have this output arrow. Before I go further, I just want to make sure everyone has this input arrow and output arrow on the Simulink block. Okay, next part, small lines. So I'm referring to the line here, this small teeny tiny arrow. So can you see this teeny tiny arrow here? And then there is another teeny tiny arrow here. Okay. Now here you can actually go to trim, you can initialize model. Initialize model. And your trim operating point will get saved in the MATLAB workspace. Initialize model, click OK. So now if you go to your workspace, your operating point is being saved. Can you see this operating point is saved? Now what I want to do is I want to linearize. And I'm gonna go here. Can you see this linearize? Click here. You can do linearization using with plots or without plots, any way you want to do it. I'm just gonna do it without the plots. So linearization with no plots. Go to linearization, linearization without any plots. I'm gonna click on this and I want you to watch what happens on your screen. Click, and then it's gonna start numerical linearization, and boom, here is your model. And can you see this A matrix that you got is exactly same as the A matrix that we derived a minute ago. 0, 1, minus 3, 0, 1, 0. Are you with me so far? This is the A matrix that we got. And it actually tells you what are the states, x1, x2, and your input channel is U1 and your output is Y1. Your B matrix is this. Do we need to load anything to mark? No. Nope. So if that happens, which means you're not trimming around the operating point. Okay, I will explain this once again from the going back from the beginning. All right, here we go. So this is question for Jade. Do you have your operating trim point in the MATLAB workspace? Okay, let's go back. Close this. Okay, model linearizer. And result viewer, model IO, trim model. Now, yeah, it's got external input specified, it got changed. Configuration got changed. Anyway, so what you need to do is you will have to go back and start from the beginning. Okay. Simulation, save, apps, model linearizer, model IOs, trim model. External input. Okay, it doesn't like this. So I will have to make the changes again. So go to Dmux, connect it over here. Connect it over here. Connect it over here. Save. No. This is the system that we started with. Go to apps. Go to model linearizer. Model IO. Let's see. Trim model. Okay. External input specified in the block. Yeah, this error shouldn't be there. Let me see if the simulation runs. Yeah. Yeah, initial states are not defined. Okay, I will have to restart and do this exercise again. But recognize what you can do is you can actually trim the model using the way I did, and then you can linearize the model by extracting the parameters. I will go through this problem once again in next class, and I will talk about how to perform this linearization and then how to use linmod to perform the same linearization. So in the meanwhile, I would encourage you to install all the necessary toolboxes that you need, and then try to repeat this exercise on your own. And that's it for today. I'm gonna stop here. and I would be happy to answer any questions that you may have.